Hey everybody, it's Tony from Adafruit, and this will be part 2 in the Raspberry Pi Talking to Wi-Fi Things series. So in the part 1 video, and I'll put a link in the description below, and this is on YouTube, so you can check out the first video. But basically this series, I wanted to look at how to take a little Wi-Fi microcontroller, like the ESP8266, or like the AT1500 Wink, or the new WISD boards, anything that has Wi-Fi. How do you have that talk to a Raspberry Pi? So things like sending sensor data from the board to a Raspberry Pi, or even having like the Raspberry Pi send commands to the board, like turn on LEDs or sensors or actuators or things like that. So it's something that's not immediately obvious. So there's really good example code of like how to run a web server on these little boards. But I wanted to go through just some of the basics of different tools and utilities you can use, and then eventually we'll start looking at like code you can write to control these different Wi-Fi boards using a Raspberry Pi and eventually some Python code, but for now we're just using some simple little tools like Netcat. So definitely check out the first video if you haven't seen it yet. It's a great little kind of introduction to some of these useful tools. In the first video, we basically showed how to take a little sensor connected to an ESP8266 Wi-Fi board and have it send its sensor data. It was a little humidity sensor. Send that data to a Raspberry Pi, actually with no coding on the Raspberry Pi. So we used a really neat tool called Netcat that we'll actually use again in this video to play with. So in this video though, I wanted to kind of follow up. So the first video, we looked at how to send data from a little Wi-Fi thing to a Raspberry Pi. And in this video, I wanted to look at going the other way. So having the Raspberry Pi send data to a Wi-Fi board, like send a command. You might imagine the board having like an LED, and you could turn like, send an on command or an off command that turns the LED on or off. So, real basic kind of simple thing, but, just with sending commands to a Wi-Fi thing and having that Wi-Fi thing send data back to a Pi, there are a lot of possibilities for cool things that you can do with that. I mean, you can build, really a whole self-contained device, have multiple devices, like multiple Wi-Fi things, all controlled by a central Raspberry Pi that you have, that's like logging sensor data, sending them commands, stuff like that. Your Pi could be like a gateway to the internet that, receives commands over the entire internet. So just lots of cool possibilities, and we're going to slowly build on this series as we go with it. So let's just kind of dive in and get started. And there are a few things to start with that I'll show. Let's jump into kind of the main view. So up in the right corner here, I just have, this is the Raspberry Pi. This is the Pi 3, but honestly, any Raspberry Pi will work. I have it connected to my network through Ethernet jack, just because it's simple and I like to do that one. And then right here, this is the Feather Huzzah ESP8266. So this is what we used in the previous video, but it's set up a little bit differently. So there's a little LED connected to it. It's connected to pin 2 on the ESP board. And so the goal of this video is that I want to be able to have the Raspberry Pi send a command to the ESP8266 and tell it, turn on or turn off, basically, so that you can control the LED just with some simple commands. So let's kind of dive in here, and then also the GitHub repository I'm looking at right here. This is the source code where I'm putting all of the code for the examples. So the first video, part 1, I have, it's an Arduino sketch that we created, and it gives you a little bit of a rundown of like what are the different netcat commands you can use to control this. So part 2 is what we'll look at here. And maybe before we get into part 2 though, I wanted to just show a quick little follow-up from part 1. So in part 1, I showed how to log sensor data to CSV, a comma separated file, just using simple netcat command and piping that to some utilities. And I just want to show a neat thing that you can do with that. So I'm looking at Google Spreadsheets, and the reason why I save that data as a CSV, a comma separated format, is that you can actually just import it directly into Google Spreadsheets, or really any spreadsheet app. Like Excel does this. Most chart kind of applications can take comma separated data. And so what we can do, if we load this data up, then we'll be able to see that you can build a chart like literally in one click. It's really simple and easy. So I just went in, and if you don't have, you need to like create a Google Spreadsheet account. I'm sure there's a free level they have, and at some point there's a quota and you have to start paying. But this is just a simple set of data. And what I'm going to do is I'm going to import data, and I'm going to import the file that I created in the first video. So it was this sensordata.txt. And so we'll import this data, and you'll see the data. At first it'll ask you, what type of data is this? And it's pretty smart. It'll actually figure out that it's comma separated automatically. So if I say import, then we should be okay here. And it spins for a second, it just loads in the data. And now you can see, okay, so it's just loaded it like a spreadsheet. So these are each of the columns. Each column is just each of the column comma separated bits of data. And so if you remember from the first video, what I'll do is I'll insert a header line above here to kind of describe the data. So the first column was the time, and so we use that TS utility that adds a timestamp, because the tough thing is the ESP8266 that's sending the sensor data doesn't really know what the current time is. It could talk to a network time server to figure it out, but it's a little more work to do that. Whereas the Raspberry Pi, it's running a full Linux operating system that already knows how to talk to, internet time servers, figure out what's the current time. So it's really easy for the Pi to receive sensor data and then throw a timestamp on there to say, this is when I received it. Now the next thing was kind of the name that we gave this. It was like a descriptive name, so that if you had multiple boards, like multiple different sensors all around your house, each one you'd probably want a descriptive name. So like, here's the bedroom sensor, and here's, the kitchen sensor. So it's good to have that knowledge in your data. And then after that was the humidity, and then the temperature data. And so the humidity is in percentage, like 100% humid. Hopefully it's not 100% humid, versus, it's normally about 50% humid or so around here. And then temperature, this is in Fahrenheit, so sorry, European folks. And then to make a chart from this, it's super easy. You just select all 4 of these columns. And because I have the time, which I want to be the x-axis, like the lower axis, as the first column, Google spreadsheets are pretty smart, and they'll realize like, oh, this must be what you want the x-axis to be. And then it also seems to pick up the humidity and temperature. But then just go to Insert Chart, and it will actually just give you a little preview here of what the data. So it kind of tries to infer the right thing. Seems to do a great job. So it figured out I've got a humidity and a temperature and time down here. So that's perfect. We'll just insert this. And that's pretty simple, just a couple clicks, and you can render the data here. So even though we're using simple tools like Netcat in the first video, just saving that to a CSV file, that's good enough to get data to visualize in interesting ways like this. It's not dynamic, it's not going to instantly update, but maybe eventually we'll get there. So if you saw the Raspberry Pi Internet Thing video series, the previous series I did, where we made a little web app that dynamically updated some charts, maybe further on in this series we might get to that point here. But this is simple and easy, and I just wanted to show it off because usually you probably don't want to look at the raw data here. You want to look at over time. What are the trends here? So like you can see, this had a few examples of the humidity kind of spiking up to almost 100% or so. So cool little thing I wanted to show. Check out spreadsheet programs, and if you're looking for a simple way to save data that you can render charts from, I like the comma separated format. It's really easy to create it, and it works well with a lot of different apps and things. So okay, so let's jump in then to this video, or part 2 here, where I want to have the ESP8266 microcontroller receive commands from the Raspberry Pi. So like to tell it to turn on or turn off the LED right here. So let's just kind of jump in. And I'll start with an example sketch. So, I'm using the ESP8266. I've already set up Arduino to use the ESP8266 Arduino kind of library or board package. And when you do that, so make sure that you select, the board. So I'm using the Huzzah ESP8266, but any of the ESP boards, make sure you select one of these. And then you can see in the examples in Arduino a whole bunch of example code here. And I was looking for a really good example of like just a simple server application. And there's not really a super simple one, but the simplest one I saw was under the ESP8266 Wi-Fi, the Wi-Fi web server example. And even though I'm not going to create a web server in this video, the basics of a server that receives a command, is basically a web server. Web server is just a command that or server that listens on TCP port 80, usually TCP port 80, but there's also SSL, which is like 443. But it listens to that, and it just receives special commands like, get the index.html web page, and it just sends it back. So, in our case, we're a little bit simpler, but the same basic idea. We want to listen on a port, and when we receive a command like, the string on or off, then we want to change the LED. So we can use this as a base to kind of customize and make our own little server here. So let's just kind of dive into it. Let's just first run their example as is. So I'll put in my Wi-Fi details, and of course everyone gets to see the password for this. So, okay, there's my Wi-Fi details. We'll keep everything the default. So this is going to listen on port 80, which is the default kind of web port. It's going to set up the LED on pin 2 as an output, and then it's going to wait for something to connect. And it's a little tough to tell from the code. They don't really describe it very well. They don't really describe it in the comments. But if something requests the /GPIO/0 path, then that will turn off the LED. And if something requests the GPIO/1 path, that'll turn on the LED. So we can go into our web browser and hit those URLs and see how it works. So, okay, first let's just compile it, and then we'll upload it to our board here real quick. But you can see, I mean, this code is not that complex, and it's actually based on, in the Arduino IDE, they have a Wi-Fi class for like the official Wi-Fi boards, and they're actually pretty old. I think the Wi-Fi boards are like from, you know, the 2010 or so. But the ESP8266 classes try to emulate the Wi-Fi classes. So, you know, there's a Wi-Fi server class, which is the same as the Arduino Wi-Fi server class from the Wi-Fi board. So you can use the Arduino Wi-Fi board kind of documentation as a loose reference here. But I think I also grabbed a link to yeah, here we go. So, and again, I'll put all these links in the description below, and this is on YouTube. But on the ESP8266 Arduino GitHub page, they actually have some really nice documentation now. And so they talk about their Wi-Fi library and how it's pretty much just a direct port of the Wi-Fi library. Gives you a few hints here and then kind of points you at the Arduino Wi-Fi reference here. So, you know, if you're wondering like what all can you do with a Wi-Fi server instance, look at the documentation there and it kind of describes it. And, you know, also, you just don't be afraid to look at the code. You know, it's really not that complex to dive into it and to see what they do. So, okay, let's see. I'm going to close this blank example because I don't need it. And then, yeah, we're going back to the Wi-Fi web server. So, okay, that compiled. Now let's upload it. Let me make sure I have the board selected. Yep, selected there. So we'll do a quick little upload to it. And then this will, well, I'll open up the serial monitor and it'll do a little bit of serial output. It'll tell you once it connects to the Wi-Fi network. And then the important thing is it'll tell you the IP address of the ESP8266 board. Because remember from the first video, you know, the IP address is how you identify something on your network. And you need to know that to talk to something. And you might not know the IP address. Like you might know, you know, the host name, for example, like, or DNS name. And that's okay. As long as something can resolve to an IP address, then it'll work. So, okay, that uploaded. Let's open the serial monitor. And it's an 115200 baud. And let's see, I'll reset the board just because the ESP, it's so quick. It usually connects to your Wi-Fi network before you can even open up the serial monitor. So, okay, so it's connected. And this is the handy thing. It prints out, here's the IP address of the little ESP board. So I'm just going to go into my web browser here. And let's go to HTTP, that IP address, and then /GPIO/1. And when I go to this, we should hopefully see that look at that, the LED turns on. And you get a little response back that says the GPIO is now high. And if I set this to 2 or to 0, then we'll see LED turns off right there. So pretty cool, pretty simple. And you know, this is almost what we want to do, but I don't necessarily want to create a web server, you know, just yet. Like it might be useful to create a web server on this, but I want something even simpler that I can just blast a string at, you know, using netcat, like an on or off command, and then, you know, it'll respond accordingly so that you don't have to use a web browser or something like that, you know, because eventually I could have Python code running on the Raspberry Pi that's, you know, sending an on or off command to this little Wi-Fi board here. So, okay, so this example works well. This is pretty straightforward. So let's just kind of start modifying it a little bit to suit our needs a little better. So I'm going to first change, instead of using port 80, let's use port 5000. Just because, you know, like I said in the first video, a lot of those lower numbered ports have a specific meaning. Like port 80 means this is a web server, and I'm not really creating a web server here. So, you know, I could use port 80, but it just could be confusing. If, you know, something finds this device and sees that port 80 is open, it might think, oh, I should talk, you know, the HTTP protocol, when that won't really work in this case. So, okay, so let's go through this setup then. The setup is pretty simple. It's mostly boilerplate. You know, you initialize the Wi-Fi on the ESP board, make sure that you connect to it, and there's a little bit of a loop to wait and see that that happens. And then you basically just call server begin, like that does the initial kind of initialization of the server. So that'll create, like, it'll listen for connections on the port that you specify up at the top here. So, you know, this port 5000, it'll start listening for connections. Then it prints out the IP address here. So that's, you know, the handy thing that we see in the serial output. Now in the main loop for this, so this is where it starts to get a little interesting. And again, this follows the convention of the Arduino Ethernet library and Wi-Fi shield. So they kind of have this idea, when you have a server, you call this .available function and it'll return a client instance. And if this client instance evaluates to true, then it's good. You have a connection and you can start sending and receiving data with this client. If it's false, if it evaluates to false, then it means there's nothing connected yet, and you know, you should like go do other processing or delay a little bit, or just, you know, return back to the loop to try again and wait for something to connect, because, you know, this thing doesn't really do anything until something connects to it. So that's effectively what we're doing right here. So I think this is a fine check. You know, we're basically just saying get a client. If there's no client connected, you know, if it evaluates to false, then just return back, and so the loop will start over, and it's going to, you know, check again to see if something's there. So most of the time your code's going to be spinning in this loop right here, waiting for something to connect. But once something does connect, then it's actually going to continue on and start to do some of the other code here. So it's actually going to say, it'll print out on the serial port, hey, some new client connected, and then it's going to wait to see until the client.available is non-zero. So that means that there's data ready to be received by the client. And it just kind of spins in a loop here waiting for that. And then what it'll do is it'll call this client.readStringUntil function, and it's going to read the string until a carriage return, the /r. And this is kind of part of the HTTP protocol, where you send a line that's kind of the command, like I want to get the index.html, and then you end it with a carriage return and a new line character. And so it's kind of waiting for that to receive that bit of data, and then it'll go on and process it in here. So, you know, that's kind of what that part's doing. Then this part is actually looking to see, okay, I received a full line. Now let's see, you know, does that line start with, or does it have, you know, GPIO/0 inside of it? So if you did like a GET request against that, then this would evaluate to non-1. And they're basically looking to see, did you send GPIO 0 or 1, and then they'll set this value accordingly for it. And if you didn't send one of those, it'll actually print back and say, oh, I got some invalid request, and it'll just close the connection and return. So if you did send one of these, though, it'll continue on. It'll actually change the LED, so do a digital write on there. And then it'll print back a response. And the response that it sends back is using kind of the web, the hypertext transport protocol. So it sends like a canned response back that says, you know, this is a 200 OK response, everything succeeded. And it sends a quick little HTML thing that says, you know, here's the current value of your GPIO pin in this case. So, you know, I'll maybe start from the bottom up here. And once it's done sending this, you know, it basically just finishes the loop. And they actually have a comment here that kind of explains. So once the loop ends, it'll start over again, and it'll go up to the top, and it'll actually disconnect your client, because this Wi-Fi client instance right here is a local variable to this loop context. So, you know, as soon as the loop starts again, as soon as the loop function exits, any local variables kind of get destroyed. So, you know, their destructor is called, and so I'm assuming inside of there it disconnects the client. So it's just good to know, like anywhere you see this loop returning, you know, like in the error case here, that actually means it's going to disconnect the client. So it's not super obvious, but it's a good thing to know. And if you didn't want to disconnect the client, then you'd need some way to, you know, remember these clients. So you'd need to pull this out of your loop and maybe have it as like a global variable. But then you need to think about like what happens when like multiple clients are trying to connect, and so like how many clients do you want to support connecting to your server, which gets a little tricky. And so this server really doesn't support multiple people connecting at the same time. And I think that's okay, because, you know, our general thought is that I just want something to connect, send a command, and then disconnect. You know, I'm not going to have it sit around and listen and receive a bunch of data. You know, maybe in later videos we'll look at something like that, but I'm just keeping it simple and just letting it send a command and exit out of here. So, okay, so let's start from the bottom then. I'm actually going to remove this response that it sends back. I don't need it. I can send my own response. I'm going to remove this serial output because I don't really need it. This client.flush, you see this a lot in here, and this is basically meaning if there's any data queued up to send to the client, make sure that it finishes sending before you move past that flush command. And so it's just good because like when you do, for example, let's see, where is like a client print? If I did like client.println hello, there's actually a little bit of asynchronous stuff happening here where these bytes get thrown into a buffer, and then the ESP Wi-Fi hardware will send that data out. And so, your code might continue on and go do other things while that data is still sending out a little bit. And if you get to a point where like maybe you disconnect the client because your function is done, if it didn't finish sending that data, it'll get cut off and you won't actually get the full response. So that flush call basically says, okay, finish sending all the data, make sure the buffers are empty, and then move on. So it's a good thing. Anytime I send data back to the client that's connected, I'm generally going to want to flush right after that, unless I know that like I'm doing something that's going to take a lot of time and I don't really need to worry about waiting for that. So just good to be aware of. The GPIO, I'm going to remove this for now just because we'll put it in our code for turning the LED on and off. Matching the request, I'm going to show a different way. So in general, kind of how they're doing the string processing here, they're using this read string until function, and this is a part of the Arduino stream class. And again, I'll put a link in the description below. This is the documentation for it. And so you can see this read string until function, super handy function. Like if you have a stream-like object, which the Wi-Fi client, this is a stream object, and it's not obvious, but if you look at the classes and how they're defined, it's a subclass of the stream class. And so you can call read string until, you give it a character that's your terminator, and it will just read bytes. It'll wait, read bytes until it finds that terminator, and then it'll return back a string to you that has all the bytes that it read up to that terminator. And it actually has a timeout too, which is super handy because, again, you got to think about, when you have something connected to you and you're waiting to receive data, what happens when that thing doesn't give you data in the time that you expect. So, you don't want to just sit there in an infinite loop because then you've effectively bricked your ESP board in the sense that, like nothing else can connect that thing because you're stuck in this loop waiting for some old client that might not even be connected anymore to send data. So, it's good that this has a concept of a timeout. So, and I think the default timeout is 1 second, but they actually say you can call the set timeout function if you want to change this, like 5 seconds, 10 seconds, something like that. But I think 1 second is okay because if something's sending a command, it should be pretty quick. Like we shouldn't have to wait around. It might not be fast enough for like me, connecting to it myself manually and typing things in, but certainly fast enough for a script that sends it a command. Now the big thing though, so this is using the Arduino string class. So it doesn't really show it here, but you can see in the code it's returning a string object. And this is a little bit of a contentious thing with Arduino. So the string class tries to be like the string class in the C++ world, in the standard library for C++, where you have a string object and it could be a string of any length. This could be like a 10 megabyte text file, although it really couldn't because there's not that much memory on the ESP. But as far as the string class is concerned, it can be any arbitrary size, which is difficult when you're on these little low memory microcontrollers. The ESP, boy, I forget how much memory the ESP has. I think it's like 32K of memory or maybe 16K of memery. It's not a lot of memory. Certainly way less than your computer. So you need to worry about things that use that memory. And this memory, it doesn't come for free. It's there's not like a garbage collector that'll give you this stuff back. Internally the string class, because it doesn't know how big the string is that you want to use, this read string until, it might read only like one character. Maybe you send like a single character and a carriage return, in which case it only needs a buffer of 1 byte or 2 bytes maybe for the null terminator. Or it could receive 10 megabytes of text, until it receives that end line character. So it doesn't know how much data is going to be there, so it has to use dynamic memory, which is using things like new and delete or malloc and free in C. And that basically means, you can call, whenever you use new in C++, you're creating a new instance of something, and you're putting on what's called the heap, which is, just a place for dynamic memory. It's just a big pool of unused memory, and you can basically say, hey, I need, 20 bytes of memory. Give me a chunk of 20 bytes. And, the new function, or malloc in C, will go and look at the heap, and it's a special data structure that says, okay, here's a 20-byte block of memory. I'm going to tag this as your bit of memory, and here you go. Here's a pointer to it. Go wild with it. The problem comes in that, if you're doing this a lot, you can use up that heap very quickly. Imagine if in a loop I was just constantly asking for, give me a 20-byte buffer, give me a 20-byte buffer, over and over and over again. That's at some point I'm going to use up all of the memory on the ESP8266, and then suddenly when I say give me a 20-byte buffer, the function's going to fail. It's going to say, uh-oh, I don't have enough memory. You're on your own. You better figure out how to deal with this. And that can cause a lot of problems. If you're lucky, you get like an error back and you catch that error and you can handle it, and maybe you can go and get rid of some unused memory that you were using before, and maybe you can allocate more memory. If you're unlucky, maybe the whole chip just resets itself because it doesn't even handle that kind of a case. So, you get all kinds of funky situations like that. Now, it's even worse on the normal Arduino boards like the Uno, because they only have 2 kilobytes of memory. And so it's very easy to go through that memory. And, you might actually be doing all the right things. Like you might be, getting a new chunk of memory, and you might be freeing that chunk of memory when you're done with it. But even that can run into problems because, if you're grabbing just randomly sized chunks of memory, remember the way that the new and the malloc operators work is that they need to find a contiguous block of memory that's that size. So like if you say, hey, give me a 20-byte long block of memory, it has to find a block of memory that is 20 bytes long at least. And so imagine a case where like you ask for a lot of small chunks of memory, maybe like 5 or 6 bytes of memory, and that's really easy. Malloc can go through and find all kinds of little spots to give, little 5-byte chunks of memory, and maybe you stop using those and you call delete on them or you call free on them, and that tells, the memory system that I'm done with this little 5-byte chunk of memory. If something else wants 5 bytes, go for it. I'm not going to use it anymore. But now, imagine you've got your memory and you've got all these little 5-byte chunks of memory that were used and now they're free. And then something comes along and says, I need 16 kilobytes of memory. I need a lot of memory. And now your memory allocator goes through and it says, okay, where can I find a block that's 16 kilobytes long? And it starts looking at all of its memory. And if it's smart, it might realize like, oh, I've got all these little 5-byte chunks that are all next to each other. And, just so happens they're not being used anymore. So I'll just reclaim all those and, there I can find 16K. But, if even just one of those little 5-byte chunks inside of that 16K block is in use or can't be reclaimed, then you're kind of screwed. You can't get a 16K block of memory, and your memory allocation is going to fail. Even though technically you might have more than 16K of memory free, you don't have enough free to give to the function that's asking for memory. So long story short, it gets tricky when you use dynamic memory, and you need to be careful about these kind of issues because it's not the kind of thing that will like immediately fail and you'll instantly know, oh, it's the first time this runs, it fails because it runs out of memory. It's the kind of thing where your code runs fine for a little while, and then once the heap gets fragmented, then you start to see, uh-oh, now it just randomly fails, and I can't figure out why it's randomly failing. Maybe it's randomly locking up. So it's a very subtle thing that when you run into it, you're going to bang your head against the wall for a while. So what I like to do to avoid this is to use a buffer of memory that I've allocated once ahead of time, so that I don't need to reallocate this all the time. And so that's why I don't like to use the string class for stuff like this, because underneath the covers, if you look at the implementation of it, it's using dynamic memory. And so, you might not realize it, because just by looking at this code right here, I don't see any new or delete statements. I don't see malloc. I don't see free. So I don't really know that this is using dynamic memory unless I've looked at the class. So I'm going to show a different way to deal with this kind of situation. Like we'll create a character buffer and we'll use some functions to fill it with data up to a point. Like, we'll limit how much data we can throw into this buffer, because I only want to receive simple commands, like the string on or off. So that's like 3 or 4 characters. So it's not a lot of data that I need to receive. So I could have just a small buffer that's a few bytes big and just read the first few bytes of a response from the client that's connected. So okay, so let's just kind of redo this logic then. So what I'm going to do is I'm going to create a buffer, so like just an array of bytes or characters, and let's call this received. And I'll make this 5 characters long, because the 2 messages I want to receive are the string on or off. And so I need a buffer that's at least big enough to hold those messages. So 5 is a good point. And I'm going to do this equals curly brace 0 syntax. So this is just kind of a nice little C++ shortcut to say initialize all of the data in this array to 0. It can sometimes be ambiguous, like in C, if I remember correctly, arrays don't get initialized to 0. So a lot of times you'll see people use memset, very handy function. You can say set received to the value 0, and you have to give the size. So this is 5 bytes long. But effectively, this line above, the curly brace 0 is saying initialize all the members of this array to 0, which is what I want. Like, it's a null value, which for a string buffer is usually what you want to have. Because remember, like a C-style string has to end with a null character to say this is the end of the string. And we're going to use some C string functions below that will want this to be true. So okay, so that's our buffer of memory. Now to read the memory, there's another very handy function in the stream class. So you saw read string until. Read bytes until is what we want to use. And so this one's a little bit different. It takes in some more parameters. Basically, you give it a character to look for, the terminator character, just like read string until. Then you need to give it a character buffer, so like an array that I just created of characters, and then give it a maximum length. This is the size of your buffer, like the at most how much data can this return back to you. And so this function is going to run until it receives either the terminator character or the length number of characters, whichever one happens first, it's going to terminate and return back. And then it's just going to copy into your buffer all of the data that it's received up to the termination condition. And it also has a timeout on it too, so that it'll wait up to a second, and if it doesn't receive any data, then it just stops, and we can catch that case. So I really recommend using these kind of functions like read bytes until versus the string class. There's some certain cases you can use the string class, and you can actually tell the string class to pre-allocate a certain amount of memory so that it's not dynamically allocating all the time. But it gets very tricky to do that right, because it's super easy in C++ to get a lot of these dynamic allocations and not realize it when you're using the string class. Because like if you add 2 strings together, like if you have string plus string, the way that the classes are implemented and the way C++ works, it can create a new string object, and that's going to allocate memory. And so you might not even realize that it's happening until your program crashes. So okay, so let's use read bytes until. So let's do client.readbytes until, and it takes in the terminator character. So I'm going to do /n, a new line character in this case. And then it needs the buffer, so that's received. It's just this character array. And then it needs how many characters to read at most. And I'm going to give 4 right here. So, I initialize this as an array of 5 characters long, all set to 0. But I'm telling read bytes until only read up to 4 bytes. And that's just a good best practice, because that means that the last byte, that 5th byte, will always be 0, and read bytes until will never overwrite that. So at the very least, I'll know that this is always a proper C string, like a null terminated string, which is a good safety check, because that's one big problem with the C programming language, in general, that if you're not careful about like ending your buffers with a null character, and if you pass that buffer to a function that expects to see a null at the end and it doesn't find one, it will go off into other bits of memory and start processing it. Maybe it'll just read that memory, or maybe it'll write to it and just crash your program. So, easy to shoot yourself in the foot. So you always have to be careful about this. And, really a smarter way to do this would probably be to say, let's make a define that's like, received length, and then set that to 5. And then let's say, here's the size of my array here, and then let's actually do received length -1. So that'll work too, and that's a little nice. Now there's only one spot that I need to change the size of this buffer, and I don't need to go back through and remember like, oh, if I increase this buffer, I need to change this value, and I need to make it 1 less. So it's smart to do things like this, to have like magic numbers or constants like this in one spot so that it's easier to change them. So okay, read bytes until. Now read bytes until it will actually return back a 0 value if no valid data was found. So normally it'll return back how many bytes of data it received, but if like the timeout is exceeded, then it'll return back 0. And so I want to catch that case. So let's put this in an if condition. So if this equals 0, then basically the timeout was exceeded. And in this case, I'm actually going to have it print out to the connected client. Let's do a print line error timeout. Just to tell the client like, hey, I waited and you didn't give me anything. And then to be smart, let's do client.flush just to make sure that that error message gets sent over. And then let's just return. So that's going to exit out of the main loop. And as a result of exiting the main loop, the client is going to get destroyed and it's going to close the connection effectively. So it'll close the connection and they're going to have to reconnect and try again basically. So let's keep that. And now let's just let's delete this next check here. So that was previously like looking at the string and trying to see does it have that GPIO line. But now things are a little different. So I'm not using the string class, I'm using a character buffer. So when I want to look at what's in this character buffer, I'm looking for a command. I'm looking for either on or off. And an easy way to do that is to use some C functions to compare two strings. So if I can compare my received buffer string to the string on or the string off, then that's an easy way to see if a command was sent to me. So let's do that. We'll basically add in some new if conditions here. So let's do if. Now to compare strings, and again I'll put links down below to these web pages I'm looking at. Basically the C standard library has all kinds of super useful functions. One is called strcmp, string compare. Very simple. You just pass it two strings, and these have to be null terminated strings, and it's going to go through each of them character by character and compare them. And if they match, it'll return 0 back. And if they don't match, then it'll actually say like which one had less characters. You can kind of tell like which one maybe didn't match what you expected. But really all I care about is if they're an exact match, the 0 case. Now, like I was saying before, you're using null terminated strings, and you have to be careful because if you pass this function a string that's not null terminated, like if you accidentally messed up and you didn't initialize this all to 0, or maybe you got the buffer length wrong and read bytes until overwrote that last null character, bad things can happen. It's going to go off into the weeds and read memory that it shouldn't. So a little bit safer function is strncmp, strn compare. And this one, it's just like string compare. It takes in a string and another string, but it also takes in a size, and that's kind of a maximum size. So it's going to look through each string, and it'll look at most at the number of characters you pass in. So if I pass in 3 for this num value, it's only going to look at most the first 3 characters of each string. But it's also smart enough to know that if one of those strings is less than 3 characters, if it ends with a null terminator after like 1 or 2 characters, then it's not going to go crazy. It'll just realize like, oh, okay, I've only have a string of length 1 or 2, and I'll try and compare that against the other string, and maybe they match, and that's fine. So it's when you're dealing with character buffers like this, it's generally a smart idea to use all these functions, and pretty much every function that deals with string buffers in the C standard library has a version that will look at just the null terminated buffer, and you better have that null terminator or you're in trouble. Or there's a version that usually has n in the name that says, put a maximum length on this, and if you exceed that maximum length, then stop or don't go past that. So good safety check. It's smart to be defensive about this, because sure, this is like a 5-10 line function, and you could get all your numbers and offsets correct, and you could think about like, okay, I know it can never have a non-null terminated string, or just be smart, use these functions, put a limit on how much stuff you can receive, and that'll cause a lot less problems down the road. So let's use strncmp, and let's pass in our received buffer. So this is the data we've received from our client. At most, only up to 4 characters of data, because we're passing in the received length -1 here. And then I want to compare this. Let's compare against just the string on. O, N, all uppercase. I'm not doing case sensitive or case insensitive stuff. So it has to be an uppercase on. And then let's pass in actually 2 for the maximum length, because I'm comparing against a string that's only 2 characters long. So let's just say don't go beyond 2 characters, and that'll be fine. And now if they exactly match, it's going to return 0 back. So I'll say if it equals 0. So in this case, we want to turn the LED on, and that's just a simple little digital write, and I think it was pin 2, and I'm going to set that to a high value. And then let's just do an else if case here. So exact same thing, strncmp on the received buffer. So if we didn't match on, then let's go through and see if we can match off. So we'll say off, and now this one's 3 characters long, so we'll change the n to 3. And again, it'll return 0 if they match. And now we say turn the LED off. So digital write to low. So okay. And then after this, it's just going to disconnect, like it's going to end the loop. But I was actually thinking, let's put an else condition so that, if I don't match on, if I don't match off, then we'll at least match this else. And then let's have it send back an error message, just so we know, like, okay, I got something, but I didn't know how to interpret that command. So let's just do client print line error unknown command, and then flush. And let's just return also here. So okay, so that seems pretty simple. Let's make sure it compiles, and then we'll upload it to our board, and we'll try from the Raspberry Pi to send it one of these strings. So okay, let's do the upload here. And you might be wondering, how can we send data from the Pi to the Wi-Fi board? And well, hey, it's our old friend Netcat. We'll come back and use that because we can use Netcat on the Raspberry Pi to send a string like on or off or anything else really to our board. And so I'll show you how to do that. It's a real simple little one-liner, just like I think we showed in the last stream how to send stuff with Netcat. So okay, it's doing its little upload, pushing everything to the flash memory on the ESP, and we'll see in just a second. Okay, so it's done. And now if I go back to the serial monitor, looks like, yeah, wow, it just connected already. So here's the one thing. I need to know the IP address again, because that's the IP of my little ESP8266 board. So I'm going to copy that. Now I'm going to go back. Here's my Raspberry Pi. So we're connected to the Pi, and again, I've got the netcat command. I can run nc. It gives you a little bit of info about it. Okay, so let's just try connecting with netcat just interactively with its terminal. So let's do nc, and then the IP address, and then the port. So port 5000 that it's listening on. So it's going to open the connection here, and then we should see in a second here that it should disconnect. And let's just see. So okay, so it printed out at least that we got a new client. Oh, I'm sorry, actually I forgot to pull something out. So we put in all this logic right here to say, okay, read bytes until that null terminated string. But I forgot right above that, they have this little check to see they're waiting to receive data from the client. And actually, I don't think this is really necessary, because this read bytes until is going to wait to receive data. And it's got all this timeout logic. So like right now, our code is spinning right here, like we're waiting to receive something. So if I say something like hello in here, okay, now I get back, like it says, okay, unknown command, because basically as soon as I typed hello, it started to receive data. So this client available started returning, non-zero results. And then my code kicked in to say, okay, read bytes until the end of that new line, and it received hello in the response. And then that didn't match on, that didn't match off, and so it said, hey, I don't know what this is, and returned unknown command. So let's actually just pull out this check entirely, so that the difference here is that what happens if something connects but never actually sends anything, like I just did right there. I'd like it to time out. I'd like it to just wait a second and then quit. Because like I said, there aren't multiple clients that are connecting to this thing. So if something connects and doesn't do anything, that's monopolizing all the connections. Like nothing else can connect to my board at that point. So okay, let's re-upload this now that I pulled that out. And now we should see when I connect with Netcat that it'll wait for a second, and then it's going to dump out, hopefully with a little timeout error that we see down here. So we'll give it a second to upload in here. And and if you have questions, yeah, feel free to throw them in the chat. Let's see. Yep, I don't see any questions just yet. So, okay, cool. So I think we're just about done uploading. And okay, finished uploading. And now we're connected. So, okay, let's do the exact same netcat command. So we're going to connect. And look at that. After a second, error timeout. And so basically, you know, when netcat opened the connection, the server available returned a client instance, you know, a connected client. Then it immediately called read bytes until, so it's waiting for a new line. And then I did nothing. I just sat there for a second, and read bytes until fired its timeout, so it returned 0. And then I basically said, uh-oh, you didn't do anything. So I sent back error timeout and then closed the connection. So that's what's kind of happening there. So, okay, so that's cool. So we're connecting. Now here's an easy way. If I just want to quickly send some data with netcat, let's use echo like we saw before, and we can use the pipe character. So if I echo, let's echo the string on to netcat, again at the IP address of the Raspberry Pi, and port 5000. So now watch the LED and let's see what happens. So I do that, and look at that, LED turns on. So that's cool. You know, we sent basically the string on to this. And let's change this to off. And now you see, look at that, the LED turns off. So pretty cool, like, you know, just a little one-liner. Like, you could throw this into a shell script if you wanted to send a command to this device. You know, you don't have to build some crazy Python client to do this. So it's, you know, just sending raw data with netcat over this. And it's nice in that, like, you don't have to implement like a web protocol. You don't have to use, you know, a web kind of tool to send and receive data. Like, it's literally just string commands that I'm sending here. So pretty cool. So I mean, that's pretty straightforward and simple. Like, we've taken their basic web server and just turned it into more of a simple little socket server. So that's cool. The next thing that I wanted to do is to show a good way to get around having to use this IP address, because it's kind of a chicken and egg problem. It's like, I've got this little Wi-Fi thing, but how does my Raspberry Pi know the IP address to connect to it? Like, in the first video, I showed how to give the Raspberry Pi a static IP address. So it's one that's assigned to it, and it's fixed ahead of time. And that's a good option. You could do that. I'm pretty sure the ESP supports it. I haven't used it myself, but you know, I'd be shocked if it didn't support setting a static IP address. But it's a little annoying, I mean, because you might have multiple ESP boards, and each one is going to need its own static IP. So I'll show you something pretty cool that you can use. It's called Multicast DNS, or MDNS, and it's a way to do a name query for all the different devices on your network. You might think of it as like, you know, shouting with a megaphone to all the devices on your network to say, hey, who has the name, you know, ESP8266 thing? And if something on your network has that name, it can respond back and say, oh, I do. And by the way, here's my IP address if you want to connect to me. You know, because that's kind of what happens when I say, like, you know, ping Adafruit.com. You know, Adafruit.com is not descriptive enough to tell the Raspberry Pi how to connect to Adafruit's website. You know, it needs this IP address here. And the way that this works is it uses a system called DNS, where it can connect to a DNS server and ask it to say, hey, what's the address of Adafruit.com? And that DNS server, it might know, and it might respond back and say, here's the IP address. But if it doesn't know, it can actually go up to its DNS server parent. And you can follow this whole chain up to, like, you know, there's just a few high-level DNS servers for all of the internet, which is actually somewhat of a shortcoming of the internet. And it's you know, it's distributed out to a point, but there are some of these central points, which you know, in the early days of the net, maybe not early days, but like I remember in the late 90s or so, you know, sometimes those root DNS servers would be under attacks, like, you know, denial of services, where you could take down large chunks of the internet by taking those servers down. But anyways, you know, that DNS thing is just a lookup to say, I know the name, but I don't know the IP address. And so multicast DNS is a little bit of a different style, where it's not going to a central server. It's using something called multicast TCP, where you can fire out a packet to all the devices that are just on your local network, so not beyond your router. You can send out a packet that says, you know, hey, I'm trying to figure out this name, you know, who is Adafruit.com, for example, and it's not going to be on my local network, but maybe I have a little thing like my ESP8266 thing, and it can query that. So MDNS, it's a super cool protocol, very, very simple. It's built on DNS, and the ESP8266 board, the libraries, they actually have a little multicast DNS responder. And MDNS itself, it's actually pretty complex. It's a part of the Bonjour protocol you might hear that Apple created, or ZeroConf, I think sometimes you hear it called. And it's got all this extra stuff beyond just name resolution. You know, you can create these little services that publish, you know, like a thing can say, hey, I'm a web server, and you can go out and query all the devices on your network and say, who's a web server, and your thing can respond back. But we're not going to use that. We're actually just going to use the name resolution. So, you know, instead of giving my ESP thing an IP address, I mean, it's still going to get an IP, but I want it to also be able to respond to a name so that from my Raspberry Pi, I can, you know, use Netcat to connect to that name using multicast DNS instead of the IP address. And the cool thing is, the software on the Pi knows how to talk that multicast DNS protocol. So it's going to see like, hey, I'm trying to talk to this, you know, MDNS thing. I don't know its IP, so I'm going to use the MDNS protocol. I'm going to ask all the devices on the network. And if my thing's on the network, it should see that and respond back and say, here's my IP address. So, and it's pretty simple to do this. So you want to open up the examples for the ESP board and go down to ESP8266 MDNS and look at the MDNS web server. And again, they basically took the web server example that we were just looking at and just jammed in this little MDNS class. And I'll show you how to use it yourself. So you just want to pull out this ESP8266 MDNS header. And so we're going to want to add that to our sketch. And then they've actually simplified it quite a bit. I think originally they based it on some code that I created for the CC3000, but it looks like they've actually simplified it even more. They've added more support. So at some point I need to probably port their code back to our libraries. But really, all you need to do is set up the MDNS responder. So this little block of code, it's in the setup function, so it just happens once. So I'm going to copy this out, and I'll put it in my setup function. Let's see, we'll put it down kind of at the bottom here. And so you can see, basically, you need to pass in the name to give to this. So let's call ESP8266-thing. That makes sense. And the way MDNS kind of works is that you're not going to find the device under ESP8266-thing. You're actually going to find it under ESP8266thing.local. And that .local is kind of the hint that tells the Raspberry Pi that this name is using MDNS versus, you know, it's not using like real DNS. So, you know, don't go up to those public DNS servers like to find Adafruit.com and Google.com and all those sites. Instead, go look at MDNS here. So even though you don't say .local here, you'll see from the Raspberry Pi we need to add that .local to tell it that we're using MDNS. And then it also says you can actually pass in an IP address if you want to set it, but if you don't, it's just going to use the IP of the ESP8266, which is exactly what you want. And this might fail, so it does a little error check, and if it fails, it'll print out that it failed. But that's all we need to do. There's actually nothing else we need to do. I think in the background they create a little task or something in the RTOS on the ESP that's servicing this, because there is some logic that needs to happen. Like the ESP board needs to listen for these MDNS requests and needs to respond back when it finds them. But the cool thing is the library hides all that. You don't need to worry about that. So that's all we need. So let's just click compile and let's upload this. And just to kind of show you, so because, well, and actually here, let's change the name, because I've run this sketch before, and so my Pi might already know the IP address. So like if I ping ESP8266-thing.local, it might work or it might not. Let's see. Looks like it's not working, so that's probably a good sign. So okay, so good. My Pi doesn't know about this ESP thing address. So now let's upload it to our ESP board, and we should hopefully see that this might behave a little differently. So hopefully, you know, we should be able to ping the device, and then we should even be able to use Netcat. So we'll give this a shot. But you know what I really like about this MDNS is that it's simple. Like if I had a bunch of different little devices, I can give them all unique names, you know, and then my Pi can just know, like, okay, you know, I've got my bedroom sensor, my kitchen sensor, and so I might want to go and send them different commands, or you know, maybe I have like the blinds, I want to roll them up or down or something like that. So you know, each thing can have a unique name, and you don't need some central registry somewhere. You don't need like a DNS server that knows that. Each, you know, your Pi will just go out and ask, like, is, you know, my bedroom sensor thing on the network, and it'll respond. Okay, so that finished uploading. server's running. Now I don't care about the IP address, so let's just start simple. We'll try to ping our device and let's see if this works. So, okay, cool, look at this. So it changed. So, before you saw the ping failed unknown host, so it didn't know how to resolve that name. And now it figured it out. So it actually went out, queried, it sent out a request to my network to say, who is ESP8266-thing? And my little ESP board here, it picked it up, and you don't really see any output here, but it saw that request and it said, oh, I'm that thing, and here's my IP address. And then my Raspberry Pi said, okay, now I'm going to remember when something asks for ESP8266-thing, use this IP address and I'll be able to access it. So, okay, so now let's try our netcat command. So let's do echo on to nc, and now let's do ESP8266-thing.local, port 5000 again, and look at that, turns on. So we've got the LED, and then let's do turn off the LED. So off. And there we go, turns off. And maybe I didn't show it before, but let's just send some garbage command just to show that you get a response back. So we'll just say like foo and send it to the ESP8266-thing. And so here you see it does nothing, like you don't get anything back here for it. So that's pretty cool. Like, we've created a thing that you can control from your Raspberry Pi just using simple little netcat commands here. So just firing off, a little string of text, and you don't need all this overhead of like, a complex like a web protocol or things like that. The code for it is relatively straightforward. It's just waiting for a client to connect. It will read, up to a few bytes of data, throw it into a little buffer, and then check and see, what did I receive? Did I receive on? Did I receive off? You could add all kinds of extra command processing to this, like, if I had a bunch of different devices connected to this, I might have, more than just an on and off command. And the basic idea is the same. I mean, you just need to add extra conditions here to check against. Now, you need to be careful in that, like, if you're receiving more data, maybe the Pi is sending it like, a color or like a string of data, like, RGB color or something like that. You're going to need to think about, like, how big does my buffer need to be? And you're going to need to, like, do some string processing inside of here. So, maybe you want to look at if your command starts with like set color, and then you want to parse out the next like 6 characters as like hex color data. Again, go back to the C standard functions for dealing with strings. So there are all kinds of functions in here for like tokenizing a string, comparing, looking for a substring inside of a string. So go back, check out those functions, and you'll see lots of ways to process that data. But I think that's it. I think that's what I wanted to show for this series, or for this part 2 of the series. So part 1 we showed how to send data from the Pi to our thing. Part 2 I just showed how to send from the Pi to our thing, like send commands to control it. All just using netcat, simple stuff. So we're gonna keep going. I'll have maybe 1 or 2 more videos in this series, and we'll see kind of how to now do things programmatically. I think in the next video, I want to look at like writing a Python little socket server so that my ESP board can send data to Python code instead of just netcat. And then let's also look at like how can Python code send commands to my Wi-Fi thing, effectively doing what netcat is doing right now. So if folks have questions, maybe throw them into the chat, and I'll jump back to the main view here real quick. So let's see. Could you have a blink speed? Yeah, you could totally send like a parameter in here to say, like instead of just on, maybe if it sends like on and then like a number, like 120, I don't know, like millisecond delay or something like that. But again, it gets tricky when you need to do string processing, especially when you need to convert from a string that's a number into the actual numeric value. And there are lots of C functions you can use to do that you want to look at. There's like A2I or I2A, which kind of tells you, given a character, convert it into the numeric value. You could use that, but yeah, it's a little tricky, and you know, it can be annoying sometimes to deal with to string processing. But yeah, you could totally do that. But like I said, just be careful about making sure your buffer is big enough. And remember, like your buffer, it's limited by how much memory you have on the board. And so, you know, this ESP board has a lot of memory. So I could easily have, you know, like 4096 characters, like 4 kilobytes of data for a buffer. And so, you know, you could receive a big command and do a lot more processing and parsing and stuff on that if you needed to for that. So, and then, oh, good question. Would switch be faster or smaller than an if-else? Yeah, so you might be wondering, like, can you replace this kind of little, you know, chain of if-elses with a switch statement? And you can't really, unfortunately, because switch in C can't work on a string. You know, I can't have a string and then say, you know, in the case that it's equal to this value, run this code. And then in the case that it's equal to this code, this value, run this code. So you really kind of have to do these chained if-elses because, you know, ultimately you need to call that strncmp function multiple times, like once for each thing that you're comparing against. And, you know, as soon as I find one that matches, it can end. So, you know, these are all a part of an if-else block. So, you know, if I had more conditions further down here, and if it matched this top one, you know, it's only going to run that code for it. But yeah, unfortunately, you can't use a switch. But, you know, one thing you could do, like if there's a lot of processing that you're doing inside of these functions, you know, instead of writing all that code in line in the if statement, just make a function that's like, you know, handle LED on and have it call that function instead of putting all your logic in here. And then that way your big list of if conditions is a little more compact in that, you know, it's just calling a function when it matches. And then your function can be as complex as you want. You can throw in anything in there. And that helps keep it to be a little less gnarly and, you know, lots of data. You could break this out into like multiple functions that are each having their own string of, you know, strncmps. You know, like maybe you have different types of commands and there's like a, you know, parse your LED command function, and you know, you could do that. You could break things out. But yeah, good point that like it can be a pain to maintain these big chains of if-elses. So, you know, try and keep things simple generally. So I think that's it. I think I'll end the stream. You know, subscribe to youtube.com/Adafruit. You'll see this video and all kinds of other fun videos. Subscribe to twitch.tv/Adafruit. You can see me stream this stuff live. And then I like to do a stream every Monday and Friday, and I'm starting to do even some during the week. So Monday I'll do another stream. I'm thinking of looking at some interesting software, maybe this Home Assistant.io on the Raspberry Pi. And then Friday next week we'll do part 3 in this series. And so like I said before, I'm thinking let's start to do some Python code to talk to these different socket services. So that's it. You know, like, comment, subscribe, you know, do all those awesome things. Thanks for watching. Thanks for supporting Adafruit. And I'll see you guys Monday and then Friday next week. So this is Tony from Adafruit, and I'll see you guys